Hi guys, again, I had a request for a couple of questions from section 3.3 in our book. So I'm going to go ahead and try to do a couple of different type of problems that we assigned as a homework. So hopefully this will help some of you. So I want to go to section 3.3. And I'm going to go ahead and start with the problem, assignment number, let's do number 40 in your textbook, okay? Number 40. Let me just explain that they're basically, in these types of problem, they're asking for three things for each of these problems. So we're going to find them. And actually it's very nice because the way they ask the question, part A, the answer to part A will lead you to part B, and the answer in part B will lead you to part C, okay? But let me write the function first, then I'll read the instruction, see what we're supposed to do in part A, B, and C. So our function in problem number 40 is given to be f of x equals x cubed plus 5x squared plus 2x minus 8. So our function f of x is x cubed plus 5x squared plus 2x minus 8. So as you can see, this is our third degree polynomial function. Also, this is kind of a special one because the leading coefficient, we'll see in a minute why the leading coefficient, which is the number in front of the leading term, which of course in this case the leading term would be x cubed because that's the term with the largest exponent, which is what we call the leading term. So its coefficient happens to be 1. So when that coefficient is 1, these are actually a little bit more special when it comes to answering part A. So what is part A? What do they want us to do with this function? Well, the first question is, let me just read the instruction and then we'll work it for you. So part A says, list all possible rational zeros. So if you remember, there is if you read the section 3.3 in your textbook, on page, I believe it's page, let me make sure, on the almost the bottom of page 328, there is a green box and there is a theorem called rational zero theorem, rational zero theorem, and that's the theorem that is going to help us to answer part A, okay? So I'm gonna just kind of explain exactly how to get this list that they asked for, and then you understand why I said that this polynomial function is kind of special, but you can do this for any polynomial function, actually, for any degree, with any degree, okay? So right now, in part A, now as you know, rational numbers are referred to fractions. So we want to look for what's called P over Q's. So P over Q's will be your so-called possible rational zeros here. So we're going to list all the possibilities, and then we'll go to part B, where we have to actually find the rational zeros. So you can see why we call them rational, because rational numbers usually refer to fractions in math. So that's why these numbers are all going to have fractional form. Now, the P, the numerator for these so-called rational numbers, are going to come as an integer factor of the constant term. Our constant term here, of course, is negative 8. So we're going to list all the integer factors of negative 8. And those will be all the possibilities for your P's. So in this case, the P's are going to be, of course, plus or minus 1, our integer factor of every number. And then for this case, negative 8, plus or minus 2, plus or minus 4, and plus or minus 8. So those are all the integer factors of our constant term. And the key, of course, here is the word integer, because negative 8 has many factors, but there's only 2, 4, 6, 8 that happen to be integer. That's why we have to make sure we emphasize on the word integer factors. Now, on the other hand, the Q, the denominator of these possible rational zeros, the Q's, now those are the integer factor of the leading coefficient. So this is what I was talking about, that this is a special case, because in this case, as you can see, the leading coefficient is 1. Now, let's say, for example, if the leading coefficient was 4, then you would have to list all the possible integer factors of 4, which will be plus or minus 1, plus or minus 2, plus or minus 4. Except in our case, since this is 1, the leading coefficient, there is only 2 integer factors of 1, which of course happen to be plus or minus 1. So what also makes this a special is when you, so now to list all the p over q's, if you take every p divided by the q's, of course, since the q's are plus or minus 1, any number divided by plus or minus 1 will give you the same number back. So in this special case, because the leading coefficient is 1, our p over q's actually coincide with our p's, because anything divided by plus or minus 1 will be the same. So our p over q's will be just simply our p's in this case. Not every case, but in this case. And that's because the leading coefficient happened to be number 1. Okay, let me just pause here for a second. So this answers your part A. I'm going to just box this. So this is the answer to part A. So these are all the what's known as possible rational zeros for this third degree polynomial function. Now, why do we call them possible? Because as you remember, or if you don't, maybe I didn't mention it, the third degree, remember the degree of your polynomial always dictates the number of zeros, rational or not, or other types of zeros. So in this case, since we do have third degree, there must be exactly and only 3 zeros. So obviously there are 8 possibilities here. So these are just possibilities. So you cannot have 8 zeros for a third degree polynomial function. You can only have 3. So 3 of these numbers, because all the zeros are rational, which is of course doesn't have to be the case for every polynomial function, but in this case all the zeros are rational zeros, which means 3 of these 8 numbers must be your zeros. The only question is, how do we know which 3 are the zeros? And that's where the part B comes in to show us how to actually find the zeros, okay? So I'm gonna go ahead and erase right here, so that way I can have some room to start answering part B. So now we have the possibility. These are what we call the possible rational zeros, okay? So let me take this off. Okay, so now part B says, let me read the question in part B. It says to actually find all the rational zeros, okay? So now we want to actually find all the rational zeros. So notice there's only 3 rational zeros in this case. Well, we know they're all rational also because it's third degree, that there has to be 3 rational zeros. So how do we know which of these 8 numbers are those 3 zeros? So we're going to do synthetic division. As you remember, one way to see if a number is a zero of any polynomial function, we can take that number, perform the synthetic division. If the remainder, which is always the last number on the bottom, if that becomes 0, then that number is a 0. So what I always like to do personally, I like to check all the positive possibilities. In other words, I check 1, I check positive 2, positive 4, positive 8. Now, if I don't find that 0, any of those to be 0, then I go check negative numbers. I check negative 1, negative 2, and so on. Now, there is actually very good news here, because once you find, the fact that this is third degree is very helpful, because once you find 1 0 from the list, you don't even actually have to continue with the list to find the last 2 zeros. I'll show you how to find the last 2 zeros by solving a simple quadratic equation. Again, that idea only works if you start with third degree. If this was fourth degree, you would have to find 2 zeros from this list before you can stop and solve and find the last 2 zeros by solving the quadratic equation. But anyway, we'll see that in just a minute. So right now, I'm just going to start to answer part B. I'm going to start with number 1. We'll see if 1 is a 0 here. So we do perform a synthetic division. So of course, we list all the coefficients. Don't forget, if there is a missing term, don't forget those zeros as you set up the synthetic division for the term that are missing. So here, of course, nothing is missing. You have your third degree, second degree, first degree, and your constant. So we're just going to list the coefficients: 1, 5, 2, and negative 8. So we're going to perform the synthetic division. Now, if the remainder becomes 0, which is always your last number, then that means number 1 is already a 0 of this polynomial function. And if it doesn't become 0, then obviously it's not. Then we go check the next possibility, which will be number 2. So as you know, the way synthetic works, you drop the first number down, then you multiply these two. 1 times 1 is 1. Then you add these two numbers together. 1 plus 5 becomes 6. And you're going to repeat the process until you pretty much run out of numbers. 1 times 6 is 6. 6 plus 2 becomes 8. 1 times 8 is 8. And 8 plus negative becomes 8. Now look at that. We got very lucky our very first trial, in this case, the very first synthetic division already give us the first 0 here. Now, this doesn't always happen, or it doesn't happen too often. Sometimes you have to do at least 2, 3, 4 synthetic before you find your first 0. But the good news here is not only we find our first 0 with the first synthetic division, but also we don't have to worry about any more synthetic, because as you remember, when you start with a third degree and you perform synthetic division, the quotient, which is given by these numbers, is always 1 less degree than your original function. So if your function is third degree, now the quotient, which was given by these 3 numbers, is only second degree. So all you have to do in this case, take that second degree equation, which remember becomes in this case x squared plus 6 times x plus 8, and you're just going to set that equal to 0, and then just solve that quadratic equation, which I'm sure takes us back to a couple of months ago when we talked about solving quadratic equations. So the solutions to this equation will be your last 2 zeros for this third degree function. And this process always works. If you start with a third degree polynomial function, all you have to do is find 1 0 from the list, and then the last 2 zeros you can solve by you can find by solving this quadratic equation, which come from the quotient in your synthetic division. And most of the time these are factorable. So in this case, I'm going to try factoring, because factoring, as you know, is the quickest way to solve a quadratic equation. Now, sometimes, of course, you can't factor, so you have to go to other methods. But for now, let's try. So, of course, to achieve x squared, it's going to be x and x. Now, you want 2 numbers such that their product is positive 8 and their sum is positive 6. So you want 2 numbers such that when you multiply, you get positive 8, and when you add, you get 6. I believe the 2 numbers should be 4 and 2, because 2 times 4 is 8, and 2 plus 4, of course, becomes 6. So now all we're going to do, as you know, this is the one we call the 0 factor property. So you have product of 2 factor is 0, which means 1 has to be 0. So, sorry, let me move this up a little bit so you can see it. So there we are. So we have x plus 4 times x plus 2 equal to 0. So now I'm going to actually erase my P over Q's here. So that way I can go upstairs and show you how to finish this equation here, or solving it, okay? So let me just take this, because we already got the P over Q. I'm sure you can go and rewind the tape and see those again in case you have question about your P over Q's, which was the part A. So now we're going to move this over here. So from there, of course, either x plus 4 is 0 or x plus 2 is 0. As you remember, this is what we call the 0 factor property, which is a method in solving quadratic equations, which means either x is negative 4 as you move the 4 over. Don't forget to change the sign, or subtract 4 from both sides. Either way, you get x equal to negative 4. Also here, as you subtract 2 or move the 2 over, and which should give you x equal to negative 2. So if you remember, our first 0 we found from the list was number 1. And now we found the last 2 zeros, which happen to be negative 4 and negative 2. And this method works in all of the cases where you have a third degree function. You can also, once you find the first 0 from the list, then you can just take the quotient from the bottom of your synthetic division and basically set equals 0 and solve that quadratic equation. And the solutions would be your last 2 zeros, okay? So I'm going to actually pause for a second. Let you make sure you see that. So I'm going to erase this, and I want to make sure you know how to finalize the answer to part B, because once you have found all your zeros, in this case again, the zeros are 1, negative 4, and negative 2. Oh, by the way, even though I erased the list, if you go back to the list P over Q's, you do notice that negative 4 and negative 2 are part of the list. In other words, you could have found them if you keep checking the synthetic, but again, we're talking about, of course, efficiency. So obviously you don't want to waste 10 minutes on doing something if you can do it in 2 minutes, right? So I suggest once you find your first 0, don't continue with the list and synthetic. Just go ahead and take that quotient, set that function equal to 0, and of course just solve that quadratic equation. So that way you can find your last 2 zeros a bit quicker, okay? All right, so let me just finalize the answer for part B before we do part C. So let me just remember what the zeros are: 1, negative 4, and negative 2. So I'm just going to write it here. So for part B, The answer, and by the way, every time we ask for zeros, it's always good to finalize the answer by writing the word zeros, and then equal, open a braces, which means a set, and then we're going to put all the 3 zeros we found inside the 2 braces. So the first 0 we got from the list was number 1. The next 0 we got from solving the equation is -4, and the last 0 we got again will be -2. So those are the 3 zeros for this 3rd-degree polynomial functions. Okay. Now, to actually answer, remember I said that the way to ask the question is very nice, because part A, the list gave us, of course, part B after we check the synthetic and solve the equation. Now, part B will give you part C, because in part C, they want you to actually factor the function, our original function f of x. Now, there is a theorem, which is, I believe, called factor theorem in algebra, that says anytime you have a 0 for a function, you also have a factor. And the way you get the factor, by x minus the 0. So if, for example, if the number 1 is a 0 of a function, then x minus 1 must be the factor, right? So this is the relationship between zeros and factors. So every time I talk about this, I tell my students that, of course, all my students, that zeros and factors go hand in hand. So anytime you have a 0 for a polynomial function, you also know a linear factor. So therefore, to answer part C, which says to factor the function f of x, we're just going to write down f of x equals to, as I said, your first 0 is 1, so your first factor would be x minus that, which will be x minus 1. Now the next 0 is -4, so the next factor is x minus -4, and of course minus will make that a plus, so that will be x plus 4. And then the last 0 is -2, so our last factor would be x minus -2, which will make that a x plus 2. And that is your last factor. So there it is. So now you just factored your function f of x. Of course, by using the zeros you found from part B, each 0 gives you a factor. And the way you get it is by x minus that 0. Like in this case, x minus 1, x minus -4, which becomes x plus 4, and x minus -2, which becomes x plus 2. And that is the answer to part C. So let me just box this one. This is for part C. This was part B. And of course, part A, which were the list of rational zeros. I'm just going to write them again, so just so you can have them finalized. So for part A, the answer, of course, which is what we started with, was the P over Q's, which were, in this case, plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. And those should be your the 3 answers to part A, B, and C for this particular function. And I'm sure the ones similar to this one should work the same way, but if you have, if you want to see more of them, let me know please through Blackboard, and I'll try to do another example for you. I want to go ahead and talk about another category of problems in this section 3.3, which, by the way, kind of asks the opposite question. So here they gave you the function. They want you to find the zeros. One of the questions was to find the zeros. This time it's going to be pretty much opposite. They give you zeros of the function. They actually want you to find the function. Okay, so we're going to kind of go back in the reverse situation. Okay, the reverse order, I should say. So let me go ahead and do one of those problems. But by the way, the key, of course, is we're going to use the same fact that says zeros and factors go hand in hand. So once they give you a 0 for a function, you automatically have a factor, right? So if they give you 3 zeros, they want to know the function. You just take those 3 factors that you get from the zeros, you multiply them together, some basic algebra, and then you have your function. There is only one issue we need to be careful about. So let me just demonstrate that with a quick example from one of your